All right, the last section in this chapter is on separable differential equations. And you will recognize a separable differential equation because it is normally in this form. dy dx equals some function of x over some function of y. So that when you cross multiply them, you get the function of y and dy together on the same side, and you get the function of x and dx together on the other side. What that allows you to do is just take the antiderivative of each side and solve from there. So let's do an example. I have dp dt equaling 3 times the square root of p. And so if I actually cross multiply, I will get, or if I put my p's and my dp's on one side and my t's and my dt's on the other side, I will get p to the negative 1/2 dp equaling 3 dt. And so now that the variables are separate, I can take the antiderivative of both sides. The antiderivative of p to the negative 1/2 is p to the positive 1/2 over 1/2, and the antiderivative of 3 is just 3t. If I simplify the left side, dividing by a half is the same as multiplying by 2. So I get 2 times p to the 1/2 equals 3t plus a constant. And I don't forget my constant there. So if I square both sides, I get 4 times p equaling 3t plus my constant all squared. And then if I continue to solve that, I just expanded out that binomial squared. And then I multiplied both sides by 1/4. And that's what I get. If I had more information, I could figure out what that c was, but I don't, so this is where I have to stop. All right, another example, if I have dq dt equaling 1 over 2q plus 6, I'm going to cross multiply again and get 2q plus 6 dq equaling dt. Now I can find the antiderivative of both sides since my q's are all on the left and my t's are all on the right. So I find the antiderivative of both sides, and I get q squared plus 6q equals t plus a constant. I would like to solve this for q, so you got to go all the way back to Algebra 2 when you're looking at the left-hand side and realize you have to complete the square, which means you take half of that 6 and you square it. And that gets you q squared plus 6q plus 9 equals t plus a different constant. So this constant c is obviously going to be 9 bigger than this c1 was. It was just a constant anyways, so I didn't want to have it be c plus 9 or anything like that. That just overcomplicates things. On the left, though, now I have what's called a perfect square trinomial, which when I factor it, gives me a binomial squared. So I have q plus 3 all squared equals t plus my constant. And now I can solve for q. q plus 3 is the square root of t plus that constant. And then I just need to subtract 3 from both sides, and I'm done. All right? And then one last example. Let me put up the screen shade so that you don't have to see the whole thing at once and be overwhelmed. Let's just start at the top. And we have x times dy dx equals x plus y. Now, here's what I'm going to do. You're sometimes given a suggestion as to some kind of substitution to make or something like that if it's an overcomplicated example. So what I'm going to do, and what you would have been told to do, is to replace y with u, which is a function of x, times this variable x. All right? So that the derivative of y is, by the product rule, the derivative of u times x plus u times the derivative of x. So it's du dx times x plus u times 1, which is the derivative of x. Okay? And like I said, you'll be told what kind of substitution to make if it's a complicated example like this one. So I just make that substitution. dy dx becomes what I just said, du dx times x plus u, and the y on the right gets replaced with ux. And there's a reason for doing that. And you'll see it in the next step because what you'll notice is after I distribute this x, I've got a ux on both sides. That can be subtracted out. So I'm left with x squared du dx equals just x. And so if I'm solving this I get du dx equals 1 over x. I know the antiderivative of 1 over x, so I know that u is the natural log of x plus a constant. But that's what u is equal to. Remember, I'm solving for y. I just created u based on a substitution that I was told to make, so I still need this in terms of y. So since y is equal to u times x, I'm going to take what I got for u and multiply the whole thing by x. So it will be x times the natural log of x plus that constant times x. And I'm done. And as I've said before, you can always take the derivative of this, or you can plug in x and dy dx and y and make sure that this function is actually true based on what you found for your function y. So that's the last example for today, the last example for this section, the last example for the chapter. So if you have any questions, let me know, and I will see you tomorrow.